Greetings, Chem 110H. Dr. Bevilacqua here. I'd like to go through a summary of the first law examples, and this is in an effort to try to bring everything together. We're going to look first at chemical reactions, and then we'll follow that up by looking at expansions of both an ideal and a real gas. And we're going to do this, here we're going to look at exothermic and endothermic reactions separately, and we're going to do it from the Venn diagram point of view. So first thing we can do is consider changes in potential and kinetic energy. And for an exothermic reaction, it's typically the case that the potential energy decreases, and for an endothermic reaction that the potential energy increases. And in both cases, if we wait long enough for the temperature to come back, the change in kinetic energy, which is proportional to delta T, will be zero. And so we can say overall that in the exothermic case, delta E, which is the sum of these two pieces, will be negative, and in the endothermic case, delta E will be positive. We can then look at the contributions of heat and work to delta E. Because this reaction is exothermic, heat is released, Q is negative, and the surroundings got hot. And in the endothermic reaction, the opposite is true, and heat flows in and the surroundings got cold. Work in these cases can be positive, negative, or zero. It depends on the delta Ng for the particular transaction. And because delta E is the sum of Q and W, that's why I said for the exothermic reaction that the potential energy typically decreases. And that's because the Q piece is typically much bigger than the W piece, as we saw in class. So let's move on now and consider expansions of gases. I've set up 4 situations here. The first 3 involve expansion of an ideal gas. In the first case, it's an isothermal expansion. Temperature is constant, and the volume increase comes about from a pressure decrease. The second is isobaric. Here, pressure is constant, and the volume increase comes about from a temperature increase. And the third is expansion of an ideal gas into a vacuum. The fourth case that we'll consider is expansion of a real gas. Each of these situations has been considered already in a homework or lecture. The first 3 were in homework 4. The isothermal and isobaric expansions were in question 7, and the expansion into a vacuum was in questions 1 through 6. The expansion of the real gas was covered in lecture 14. We can start out by considering what happens to delta PE and delta KE for each of the 4 situations. Because the first 3 are ideal gases, delta PE, because there's no bonding, can be immediately set to 0. In the fourth case of the real gas, here we had, in our example of the fire extinguisher, CO2 going from high pressure to low pressure. It overcame attractions, and bonding was broken, and so delta PE is positive. Now let's go on and consider what happens with the change in kinetic energy. We remember that for an ideal gas, that the change in kinetic energy is proportional to the change in temperature. For the expansion under isothermal conditions, temperature is constant, so kinetic energy doesn't change. For the isobaric expansion, temperature increases, so kinetic energy increases. In the case of expanding into a vacuum, we're expanding into empty space, so there's nothing to slow down the velocity of the gas molecules. So kinetic energy equal to 1/2 mv squared doesn't change. And we'll see that in the case of the real gases, the kinetic energy decreases, and we know that that's the case because they got cold. We can then go ahead and write down the value of delta E from the sum of delta PE and delta KE. In the isothermal case, delta E is 0. In the isobaric case, delta E is positive. In the expansion into a vacuum, delta E is 0. And in the case of the real gas, delta E is equal to 0. We can then go ahead and look at the Q and W pieces. In the isothermal case, Q must equal minus W because delta E is 0. In the isobaric case, Q must be bigger in magnitude than minus W so that KE can increase. In the case of the vacuum, Q and W are both 0. W is 0 because there's nothing to expand against. Q is 0 because delta E is 0, and W is 0. And in the case of the expansion of the real gas, if this is expanding into a vacuum, there's no surroundings. And so much like in the case of the third example, W is 0, there's nothing to expand against, and Q is 0 because there's nothing to exchange heat with. So I've gone ahead now and summarized the delta PE and delta KE pieces that we've already discussed. I want to take a step back now and consider what's going on in these 4 different cases. Situations 1, 3, and 4 are particularly interesting because delta E is equal to 0 in each of these, but it comes about for different reasons. In the first and third cases, delta PE and delta KE are 0, so their sum is 0. In the third and fourth cases, Q is 0 and W is 0, so their sum is 0. It's only in the third case where everything is 0. In the first and fourth cases, even though delta E is 0, 2 of the other terms are not 0. In the first case, it's Q and W that are not 0, but they have to be equal to the minus of each other so that their sum is 0. While in the fourth case, it's delta KE and delta PE that are not 0, but their sum is equal to 0. In the first case, this allows energy to cycle in and out. In is Q and out is W. While in the fourth case, it allows the useful property of real gases that kinetic energy can decrease and the gases can get cold and make a refrigerator. And then finally, we can see in case 2 that delta E doesn't always have to be 0. So if we heat a gas, such as, for example, heating a balloon with sunlight, work will be done in the expansion, heat will go into the system, and the kinetic energy will increase with the temperature increase. Thanks for listening.